We are discussing lasers in engineering physics. And in the last session, we tried to understand that whenever the incident radiation interacts with the atoms in energy levels, there exists three distinct processes, namely stimulated absorption of radiation, spontaneous emission of radiation, and stimulated emission of radiation. Now, in this session, we shall try to understand each of them thoroughly. The first one we will focus on is what is known as stimulated absorption. So, let us understand the basic things like this. Consider two energy levels, each having an energy of E1 and E2. Energy level 1 is having an energy E1. Energy level 2 will be having an energy E2 for an atom, such that E1 is always greater than E2. Let N1 and N2 be the number of atoms per unit volume in that energy. That is, N1 is the energy number of atoms per unit volume in level E1, and N2 is the number of atoms per unit volume in the energy level E2. Then in that case, before absorption, look at this. So incident radiations, this rho nu is nothing but the incident radiations, density of incident radiations. So that radiation is absorbed by this atom, it is trying to jump to the higher level. Now after absorption, what will happen? This will go to this higher energy level and this becomes empty. This is after absorption. Now if you carefully observe that the incident radiation consists of photons of energies equal to the energy difference between E1 and E2. So therefore the number of photons per unit volume of the incident radiation is what is known as incident radiation density, represented as rho nu. So the incident photons, what happens? It stimulates the atom in the lower energy level E1 to absorb the energy. After absorbing the energy, the atom transits to E2. So this process of exciting the atom to higher energy level by absorbing the stimulated incident photon, it is what is known as stimulated absorption of radiation. I am quickly recapping. The incident radiation consists of photons of energy equal to the energy difference between the levels E1 and E2. So the number of photons per unit volume of incident radiation, it is what is known as incident radiation density rho nu. So the incident photon stimulates the atom in the lower energy level E1 to absorb the energy. After absorbing the energy, the atom transits to E2. So this process of this exciting atom to higher energy level by absorbing the stimulating incident photon is what is known as stimulated absorption of radiation. Clear? So this process is what is known as stimulated absorption. That means this is the process where the exciting the atom to higher energy level by absorbing the stimulating incident photon. This is what is known as stimulated absorption of radiation. Okay. Now how many number of atoms get absorbed? Let us try to understand. So here the number of stimulated absorptions depend on the number of atoms per unit volume N1 in the first level E1, and also the number of photons per unit volume of the incident radiation, that is rho nu. That means then how many number of stimulated absorptions is depending on N1 as well as rho nu. Therefore, you can mathematically show it as the number of stimulated absorptions is directly proportional to N1 and the number of stimulated absorptions is directly proportional to rho nu. So therefore, together you can say the number of stimulated absorptions is directly proportional to the product N1 into rho nu. So mathematically, whenever you replace proportionality constant, you will get an equation same as equality followed by a constant. So therefore, this equation, that is the number of stimulated absorptions, is directly proportional to N1 into rho nu when it is written as the number of stimulated absorption is equal to N1 into some constant into rho nu. Here, Einstein has introduced two interesting constants, pseudo constants, as B and A and B. So because the levels are 2, energy 1 and energy 2, so 1 to 2, 2 to 1 consideration he has given. Therefore, in this situation of stimulated absorption, when you replace this proportionality constant with an equality sign, the constant he termed as Einstein coefficient. This Einstein coefficient is related to what? Stimulated absorption. So therefore, this constant, which is known as Einstein coefficient of stimulated absorption, represented as B12, that is from 1 to 2. So therefore, this equation, that is N1 into constant into rho nu, where the constant is replaced by the Einstein coefficient of stimulated absorption shown as B12, can be equated as the number of stimulated absorptions is therefore is equal to N1 into constant B12 into rho nu. This is what you have to understand. Here, the B12 is nothing but Einstein coefficient of stimulated absorption. That means what happened? The photon energy is absorbed. Once the photon energy is absorbed by this stimulated absorption, it cannot sustain, it has to come out. So therefore, this excited atom by this absorption from higher level has to transit to lower level energy, E1. Therefore, the excess energy absorbed should be emitted out. So after absorption, now the thing left is emission. So therefore, this emitted radiation again is of two types. The emission is a spontaneous emission and stimulated emission. Already we have seen stimulated absorption. So that absorbed photon has to come out. That means the atom from an excited state should come back to normal state, that is transition to the lower level energy by emitting out that radiation. That emitting out radiation process is again categorized into two processes, namely spontaneous emission and stimulated emission. If you recollect well, I told you there are three processes distinctly. Absorption is only one type of absorption, that is stimulated absorption. Whereas when it comes to emission, there is a spontaneous emission as well as a stimulated emission. Now let us now look at spontaneous emission. Now see, where is the atom now after spontaneous absorption, stimulated absorption? It is in higher energy state. Therefore, the excited atom in the higher energy state level E2, that can stay only up there up to 10 power minus 8 seconds. That means the lifetime of the atom in the excited stage is only 10 power minus 8 seconds. Therefore, that is nothing but the average time up to which an excited atom can stay at higher energy E2. This is what is known as lifetime of the excited state or lifetime of the excited atom. What happens after the lifetime? After the lifetime, the excited has to come back to lower level. Therefore, after the lifetime of 10 power minus 8 of the excited atom, it has to transit to the lower level energy level, E1, by itself. That automatically on its own it should come back, emitting a photon energy of the energy difference. Therefore, when the excited atom with a lifetime of 10 power minus 8 second at higher level has to come down after the lifetime into lower level E1 by emitting the photon with an energy equal to the difference on its own. It has to emit at its own. Therefore, what is E here? According to Albert Einstein, E equal to h nu. Therefore, in this equation, if you substitute E equal to h nu, this equation E equal to E2 minus E1 will become h nu is equal to E2 minus E1. Therefore, frequency you can calculate as E2 minus E1 by h. So, what is this process? This is a process where emission of radiation took place. How it took place? By the transition of an excited atom by itself to lower level energy. Therefore, this process where the emission of radiation takes place by the transition of an excited atom by itself to lower level energy, this is what is known as spontaneous emission because it has been done on its own. Therefore, this process where the emission of radiation takes place by the transition of an excited atom by itself to lower level energy, that is what is known as spontaneous emission of radiation. Okay? So let us understand whatever I have just now explained as spontaneous emission of radiation through the schematic approach. So before emitting the photon, see, this is the stage. It is the higher energy state. This is the number of atoms at that stage. So on its own, spontaneously it is trying to lower its energy by emitting out this photon after the lifetime. This is before emitting. So after emitting, what happens? The number of electrons in this state is, of course, are N1. So after emitting, that emitted photon will come out. Therefore, it will come back to the ground state. So in such a situation, if you calculate the number of spontaneous emission of radiation, depends on whom? Depends on the number of atoms per unit volume in the E2. That is, it is directly proportional to N2 only. So the number of spontaneous emission of radiation depends on the number of atoms per unit volume in the energy level 2, that is N2. So mathematically, if you want to show it, it can be shown as the number of spontaneous emissions is directly proportional to N2. So when you replace this proportionality constant with an equality, automatically you will get a constant. So you can write mathematically the number of spontaneous emissions is equal to N2 into constant. And that constant, I told you that Einstein has taken two pseudo constants, A and B, with respect to energy levels 1 and 2. Therefore, that constant is related to Einstein coefficient. This is coming because of spontaneous emission. Therefore, this constant, what you are getting, is known as Einstein coefficient of spontaneous emission. And it was named as, because it is coming from second to first, therefore it is termed as A21, N2 into A21. Therefore, the number of spontaneous emissions is equal to N2 into A21. So this is about spontaneous emission. There is another emission which is called stimulated emission. What is this? Now the excited atom, after being stimulated by the incident photon, transits to lower energy level E1 in a time less than 10 power minus 8 seconds. Earlier, atoms are being transited to lower energy after the lifetime. But here, the excited atom, after being stimulated by the incident photon, transits to lower energy level E1 in a time less than lifetime, that is 10 power minus 8 seconds of an excited atom. Now, how this transition of photon energy takes place? Again, E will be E2 minus E1 only. Therefore, E equal to h nu, that is h nu equal to E2 minus E1. From that, you can calculate nu as E2 minus E1. What is this process? Here in this process, the excited atom, after getting stimulated by the incident photon, transit to lower energy level by emitting the photons. Therefore, this is emission by stimulation. So, therefore, the process where the excited atom, after getting stimulated by the incident photon, transit to lower energy level by emitting the photons is therefore known as stimulated emission of radiation. Let us understand this stimulated emission in a schematic way. So this is how you can understand stimulated emission of radiation with this schematic approach. So this is before stimulated emission. This is the highest energy level, E2, where the excited atom is existing with the number of atoms at that level as N2. This is the ground level where you can say that this is energy level E1 with the number of atoms as N1. Now the incident photon radiation should stimulate this and ensure that this atom comes out. So that is what happened in the second diagram. It shows after emission of stimulated process, this is how the energy level looks like. Here it is getting freed, so there are no atoms at N2 level, and that is coming to the ground level. Transition took place. But interesting thing you have to observe is there are two photons coming out. One is the emitted photon, another is the incident photon. That I will discuss now. The number of stimulated emissions depends on whom? Here the number of stimulated emission depends on two things. One is the number of atoms in the higher energy level, that is N2, and the incident radiation density, rho nu. Therefore, the number of stimulated emissions depends on N2 as well as rho nu. Therefore, you can write mathematically this one as the number of stimulated emissions is directly proportional to N2, that is number of atoms in the higher energy state, and the number of stimulated emissions is directly proportional to rho nu, that is the incident radiation density. So from these two, the number of stimulated emissions can be mathematically represented as number of stimulated emissions is proportional to the product of this. That is, number of stimulated emissions is proportional to N2 into rho nu. Now again, mathematically, if you want to replace this proportionality, you can get a constant. Therefore, you can write the number of stimulated emissions is equal to constant into N2 rho nu. Constant into N2 rho nu. This is what you have to represent here. Now here, this constant is again Einstein constant. Again you have to recollect that Einstein for absorption and emission, two different constants he has taken, A and B. Process from 1 to 2 and 2 to 1. So therefore this is Einstein coefficient. What type of coefficient it is? It is coefficient related to stimulated emission. Therefore this constant is what is termed as Einstein coefficient of stimulated emission. That is what is represented as B21. There is B12, that is Einstein coefficient of stimulated absorption. This is B21. This is Einstein coefficient of stimulated emission. Therefore, the number of stimulated emission is equal to N2 into B21 into rho nu, where B21 is what is known as Einstein coefficient of stimulated emission of radiation. Now, if you observe this earlier diagram in this process, interesting thing is happening here. In this process, in addition to the emitted photons, there will be incident photons. So therefore, all these photons have same energy, same frequency, and they are all in one phase. So as a result, they all get reinforced together. Therefore, that will result in highly intensified, monochromatic and coherent radiation, which is nothing but laser radiation. For your benefit, I am again quickly recapping. If you see this in this process of stimulated emission, in addition to the emitted photons, there will be incident photons are also accompanying. So all these photons have same energy, same frequency, and all of them are in phase. When that phase happens, same energy and frequency means monochromatic. They are in phase means they have high intensity and coherence nature. Therefore, when all these photons, that means both emitted photons as well as incident photons, when they are all there, all these photons have got same energy, same frequency, and all of them are in phase, which means that they reinforce together. That will result in highly intensified, monochromatic and coherent radiation that comes out, which is nothing but laser radiation. So if you carefully observe the whole process, there is one absorption and two emissions taking place in a laser. One absorption process and two emission process. Now how do we divide them? The two emissions, if you take absorption and emission. What is that absorption? That absorption is nothing but stimulated absorption of radiation. Whereas if you take emission, there are two types of emission of radiation taking place. What are those two? One is spontaneous emission of radiation, another is stimulated emission of radiation. That means altogether you have three distinct processes taking place in a laser environment. So as per Einstein process, so in the stimulated absorption, the coefficient you are getting is named as B12. Remember, and also interestingly observe, this is B12 and this is B21. Both are represented for stimulation. For spontaneous, Einstein has taken a coefficient for A. So this is B12 is nothing but Einstein coefficient of stimulated absorption. B21 represents the Einstein coefficient of stimulated emission. Whereas A21, this is nothing but the Einstein coefficient of spontaneous emission. So three coefficients are there. Einstein coefficient of stimulated absorption, Einstein coefficient of spontaneous emission, Einstein coefficient of stimulated emission. This is what you need to understand. Clear? Now, we shall try to compare the differences between these two emissions, spontaneous and stimulated. Both are emissions only. How exactly they differ? How do you compare or how do you distinguish? That we shall try to focus to understand the same now. So when you try to distinguish between the two different processes of emission, that is spontaneous emission as well as stimulated emission, let us compare and understand. Please remember, both spontaneous emission and stimulated emission are trying to make the transition to happen between E2 to E1 only. Only difference is, in spontaneous emission, it is taking place when an atom in higher energy state transits to lower energy state by itself. Nobody is forcing it. So therefore, spontaneous emission is a process that takes place when an atom in higher energy state transits to lower energy state by itself. On the contrary, if you take stimulated emission, here also atom in higher energy state is getting stimulated by the incident photon and transit to lower energy state. So when you look at the first point of difference between these two, spontaneous and stimulated emission, is spontaneous emission takes place when an atom in higher energy state transits to lower energy state by itself. Here in this case, stimulated emission is taking place when the atom in higher energy state gets stimulated by the incident photon and thereby transiting to lower energy state. This is the first difference. So when you look for the second difference, spontaneous emission is independent of the incident radiation density. It does not depend on the radiation density rho nu here. Whereas here, the stimulated emission depends on the incident radiation density. That is the second difference. Spontaneous radiation does not depend on radiation density, whereas stimulated emission depends on radiation density. And the third difference, if you take, the spontaneous emission takes place after 10⁻⁸ seconds. That is, after the lifetime only it will take place. Whereas stimulated emission, it takes place within the time of 10⁻⁸ seconds. That is, this is after lifetime, that is spontaneous emission is taking place after the lifetime, whereas stimulated emission is taking place within the lifetime. And then spontaneous emission is a slow process, very slow process when compared to stimulated emission. Whereas here, the stimulated emission is a very fast process when compared to spontaneous emission. And of course, here in spontaneous emission, you will get Einstein's coefficient of spontaneous emission as A21. Here, you will, in spontaneous stimulated emission, you will get the Einstein coefficient of stimulated emission as B21. This is how you can distinguish between spontaneous emission and stimulated emission. So let us summarize what has been discussed in this session. We have seen in this session that when the incident radiation, which is nothing but a photon, interacts with the atoms in the energy levels, then I told you that there is a possibility of three distinct processes that can take place, namely stimulated absorption of radiation, spontaneous emission of radiation, and stimulated emission of radiation. For understanding all the three, we have considered two energy levels of of E1 and E2 such that E1 is greater than E2 for an atom, and let N1 and N2 be the number of atoms per unit volume in the energy levels E1 and E2 with the radiation density as rho nu. So with that background, when we looked at stimulated absorption of radiation, the incident radiation consists of photons whose energy is equal to the energy difference between E1 and E2. So the number of photons per unit volume of incident radiation is what is known as incident radiation density, represented as rho nu. Here in stimulated absorption of radiation, the incident photon is stimulating the atom in the lower energy level E1 so that it absorbs that energy. After absorbing the energy, the atom is transiting itself to E2. So this process of exciting atom to higher energy level by absorbing the stimulated incident photon is what is represented as stimulated absorption of radiation. Here in this case, the number of stimulated absorptions depend on the number of atoms per unit volume N1 in the lower energy level E1 and the number of photons per unit volume of incident radiation, that is the incident radiation density rho nu. Accordingly, we have shown that the number of stimulated absorption is directly proportional to N1 and rho nu. Therefore, we have shown that the number of stimulated absorptions is directly proportional to N1 rho nu. And when we replace that proportionality with equal sign, we have shown that the number of stimulated absorptions is equal to N1 into constant B1 into rho nu, where that B12 is what is represented as Einstein coefficient of stimulated absorption radiation. Now once the stimulated absorption takes place, there we try to understand that the leftover thing is the emission. Now emission is again two types we have seen. So if the excited atom transits to lower energy level E1, then it emits the radiation. So the emitted radiation is observed here as spontaneous emission of radiation and stimulated emission of radiation. So in spontaneous emission of radiation, the excited atom which is at the higher energy level E2, it can stay only there up to 10 power minus 8 seconds. So that average time up to which an excited atom can stay at the higher energy level E2 is what is defined as lifetime of that excited atom. Once the lifetime of the excited atom is over, it has to transit to the lower energy level E1 by itself, emitting the photon of energy. So this process where the emission of radiation takes place by the transition of an excited atom by itself to the lower energy level, it is what is defined as spontaneous emission of radiation. Here also, in spontaneous emission of radiation, we looked at the number of spontaneous emission of radiation found to be depending on the number of atoms per unit volume in the higher energy, that is N2. Therefore, from that mathematically we represented the number of spontaneous emissions is directly proportional to N2. As usual, mathematically, when we replace that proportionality constant, we replace with equality with a constant. Therefore, mathematically we have shown that the number of spontaneous emissions is equal to N2 into constant A21. That constant A21 is what is defined as Einstein's coefficient of spontaneous emission of radiation. Then we looked at stimulated emission of radiation, where the excited atom, after being stimulated by the incident photon, transit to a lower energy level E1 in a time less than lifetime, that is less than 10 power minus 8 seconds of an excited atom. So that transition energy also we represented as E equal to E2 minus E1. So therefore this process where the excited atom, after getting stimulated by the incident photon, transiting to lower energy level by emitting the photons is what is defined as stimulated emission of radiation. Here also the number of stimulated emission depends on two factors. One is the number of atoms in the higher energy level E1 as N2 and the incident radiation rho nu. Therefore, we mathematically represented the number of stimulated emissions is directly proportional to N2. The number of stimulated emissions is directly proportional to rho nu. From that we concluded that the number of stimulated emissions is proportional to N2 rho nu. By replacing mathematically the proportionality, we can write the number of stimulated emissions is equal to N2 into constant B21 into rho nu, where that constant B21 is known as Einstein coefficient of stimulated emission of radiation. Here in this process, I told you to observe that in addition to emitted photons, there will be incident photons also. So all these photons together have same energy and same frequency, and all of them are in phase. So as a result, they all reinforce together, resulting in high intensity monochromatic coherent radiation, which is nothing but laser radiation. This is what we have discussed, apart from distinction between spontaneous and stimulated emission of radiation. So comparing spontaneous emission and stimulated emission, we have understood these three different individual process in details. So this is what we need to understand. So in the next session, we shall see how to arrive at these Einstein coefficients mathematically.